Hello all, welcome to Power Electronics and Instrumentation class. Today we are going to deal with certain topics in the sixth module relating to digital instruments. Now, digital instruments are using logic circuits for the measurement of certain quantities. We are very familiar with the analog instruments and the examples are voltmeter, ammeter, etc. Now, what is the need for digital instruments? The main advantage of using digital instruments is that they have greater speed, better accuracy, resolution, and provide automatic measurements. All of these are the advantages, and the main advantage is the reduction in the operator errors. You can see over here the operator errors. Now, what do you mean by operator errors? Now, you might be very familiar that in the normal cases, when you're taking a reading, there is a chance that if it is an analog meter, if you take the case of a voltmeter or ammeter, what's going to happen? You have to you have to check the scale of the range of the particular scale, and then you need to divide the scale and check what each small division, what is the value of each small division, then you need to do some multiplication. There's a chance for errors when you're taking the reading. But when it comes to digital instruments, you get the value directly and there is only a chance for human errors to occur. That means maybe instead of 7 you might have read it as 1. So the error is reduced in the case of digital instruments. Now you can see over here there are two small block diagrams present. One is the first one is having a digital readout and the second one is having an analog readout. Now you can see over here in your first figure you are having a analog input. Then you have a ADC, a signal processor, and then the display is digital itself. Whereas when it comes to analog display, you need to you're taking your input which is in the analog format, you're converting it into DC or into a digital format using an ADC, that is analog to digital converter. That is same as in the previous case, but then again you're converting it back to the analog output and then you're giving it to the particular display. Now, the main, again, what happens over here, the main principle is quantization, that is conversion of the analog quantity to the digital quantity. Now, these portions are quite simple. We can just move directly to our main topic, that is digital measurement of certain parameters. Now, in this video, we are going to deal with digital measurement of frequency, time, and time shift. Now, here you can see a frequency counter. Now, what does your frequency counter do? You have an unknown input signal whose frequency is unknown. So, what you're going to do is that you can see this is your frequency measurement block diagram. Okay, this is your frequency measurement block diagram. Okay, I'm sorry. Right, this is your digital measurement block diagram. Now, you can see that it consists of a clock oscillator, a divider, a AND gate, and a counter. And finally, your output is going to be displayed. Now over here, what you're going to do is that you have your unknown input signal. It is going to be given to one terminal of the AND gate. And then you're going to create a gate enabled signal. Now, what was the gate enabled signal? The gate enabled signal is actually generated from a clock oscillator. So your clock oscillator is going to give you a fixed frequency signal, and it is divided according to the requirement. That is, we do not know the frequency of the unknown input signal. So correspondingly, you will change the divider output in order to get a higher accurate answer for your unknown input signal. And then you're going to give this particular signal to the AND gate. Now, we can just move to the next particular graph. Yes, over here. This is your unknown input signal. Okay, you do not know the frequency of this particular signal and you have provided a gate enabled signal. Now, you know the frequency and the time period of the gate enabled signal. Okay, you can see that it's quite a large pulse. Now, initially you are going to give a clear signal in order to reset your particular device. This is only to ensure that your gate enabled signal will be having a 0 output at the beginning. That is right before T1. Okay, so this is your correct time period from where you're going to start measuring. So before T1, you need a 0 output over here. For that, you're going to give a clear signal. You're going to give a clear signal and ensure that you are having the output as 0. Now, you can see over here that you are giving the gate enabled signal and the unknown input signal to an AND gate. You just see over here once again. the unknown input signal and the gate enabled signal, both of these are given to the AND gate. Now, you are familiar with the truth table of the AND gate. You will be getting a high output only when both the signals are high. So again, I'll just switch over to the waveform. Now, we can just see over here, when your unknown input signal and your gate enabled signal, only when both of these are high, you will be getting a high output. Again, when your unknown input signal goes low, even though the gate enabled signal is high, you will not be getting a high output. And you will get this pulse of these particular pulses in your output as long as both of them, both the unknown input signal and the gate enabled signal, both are positive, you will be getting a high output. After that, what happens? A half cycle of your gate enabled signal is over, and next it's going to move on to the zero mode. Okay, so your high or high output has been finished over here, and now you're going to get the low output at the gate enabled signal. So throughout you'll be having your output as 0. Now we already know the particular frequency of the gate enabled signal, and you can find out the time period t. Okay, so the sampling interval t is known for us, and you just count the number of cycles which are present during the time t, and then you can find out the frequency, right? Then it is quite simple to find out the frequency. You know how many cycles are there in a particular time. You just divide the time divided by the number of cycles, and you will get what is the time required for one cycle, and that is your frequency. Okay, so that is how you're going to measure the frequency. Okay, I hope it is clear. You're giving a gate enabled signal. The gate enabled signal is actually an output from a clock oscillator, and you are providing a divider. What is the need for a divider? Because we do not know what is the frequency of your unknown input signal. So you can change this time period of the gate enabled signal in order to get a higher accuracy output. Now we can just see what is happening within the divider. We can see that over here. This is what is happening within your divider. Your crystal oscillator is going to give you a 100 kilohertz output, and it's not going to be a square pulse. It's just going to be a oscillator output. And what you're going to do is that you're going to use a pulse shaper, and you are going to convert this signal into a square output. Okay, so from the pulse shaper you have got a square output, and then you're going to give this particular output to a series of decade counters. These decade counters will give you, will divide the 100 kilohertz by 10 after each stage. So you can take multiple outputs. You can see over here you're able to take an output of 100 kilohertz. Then you divide it by 10, you get 10 kilohertz. Then you divide it by 10, you get 1 kilohertz. So according to your requirement, you have a range of output over here. You have 10 microsecond, 100 microsecond, 1 millisecond, so on and so forth. Okay, so this is your particular time. Okay, according to the frequency, you have just found out the particular time period, and according to your unknown signal, that is maybe when you are placing the knob at position number 6, the time period will be 10 microsecond. Maybe you are not getting a pulse train when you're placing it at 10 microsecond. So what do? You change this particular position, you change it to position number 5, and you check whether you're getting a pulse train in your output. What is the reason? Suppose this is your unknown input signal, and you have chosen 10 microsecond. Okay, so 10 microsecond is going to come like this. So when you took 10 microsecond, you can see that your output is not going to be proper. If you take it as the AND signal, you are not going to get a proper pulse train over here. This might be your pulse train. So you have understood that you are not going to be able to calculate your frequency properly. So you have switched to 100 microseconds. And then again 100 microseconds, again it might not be enough, so you choose 1 millisecond. So according to your requirement, you will be choosing which time period you require, and this is obtained from the divider. Okay, this is obtained from the divider, and this is just a sub circuit of the divider. Okay, I hope it is clear. What have you done over here? You are having a unknown input signal, it is compared with a gate enabled signal, and you are counting the number of pulses during the high time of your gate enabled signal, and this will give you the frequency, or this is going to count the number of pulses during the high time, and you are going to get the corresponding frequency. Now, in order to get a proper calculation, or in order to adjust the value of the gate enabled signal, the frequency of the gate enabled signal, you are using a divider. The clock oscillator output is going to be divided into steps, and according to our requirement, you can take the particular output. Next, we can see how to measure time. Okay, digital measurement of time. It is similar to that of the digital measurement of frequency. You can see over here your unknown input signal, it is given to a particular flip-flop, that is to convert it to a particular signal that is compatible with our particular circuit. And then accordingly, again, you're going to take your clock oscillator circuit, you have your divider, the clock pulses, and the enabled gate. Okay, over here, this particular signal, the unknown signal, which has been conditioned and is sent through a JK flip-flop, that is called the enabled gate. Both of these are again compared. It's the same principle. You're sending it through an AND gate. You have again, you are counting the number of pulses during the high time of your enabled gate, and then you can find out the time period. It's basically the same concept. And next we have to find out the time interval measurement. How do you measure the time interval between two events? Or in other words, how to find out the phase difference between two signals? Suppose your signal 1 is the leading signal and signal 2, it is the lagging signal. We have placed a circuit. This is your signal generator. Right, this is a signal generator. Suppose you are having two pulse shapers. You are sending your signal 1 to a particular pulse shaper and a signal 2 to the next pulse shaper. Again, over here you are having a AND gate, or it can be an OR gate according to our requirement. Your crystal oscillator is giving you particular signals over here. This signal and the signal from the signal generator is being compared, and the number of pulses are being counted, and the calculations being done. Now, what do you have to do? You need to find out the phase shift or the time interval between two events. So what you're going to do is that you're going to give the two signals to a signal generator. And when your signal 1 gives a high output, your signal generator will give a signal. It will start generating an output. And when your signal 2 gives a high output, your signal generator will stop generating signals. And this time interval from where you have got the output, that is going to be measured, or it is going to be compared with the output from the crystal oscillator, and correspondingly you will be getting the particular values. I hope it is clear. Your signal 1, you are sending it to a signal generator. When your signal 1, when it gives a high output, that time your signal generator will start generating the pulses, and it will stop generating pulses when signal 2 gives a high output. And at this particular time, that means you will be having you will be having an output like this, and it is compared with the crystal oscillator, and finally the time during this particular interval, it's going to be counted, and then it's going to be measured, and you will get the phase shift between two events or two time intervals. Okay, so I hope this section was clear. In this section, we had dealt with the digital measurement of frequency, digital measurement of time, and digital measurement of time interval. Okay, in the digital measurement of frequency, basic concept is you're going to compare two signals. Okay, you are having a gate enabled signal, or maybe a signal from the crystal oscillator. This will be compared with the unknown signal, and it will be given to an AND gate. Your AND gate will give you a high output as long as both the inputs are high. And then the number of pulses during this particular time interval is counted, and you're getting the corresponding frequency or time. In the case of time interval measurement, you have two signals. Okay, you have two signals, right? And you're going to get the signal generator will start producing an output when the signal 1 becomes high, and when signal 2 becomes high, the signal generator will stop generating the pulses. And this time interval is counted and it is measured, and you will be getting the corresponding output. So I hope this section was clear. Please stay tuned for more videos. Thank you.